All right, guys, we're going to get started in physics, and to start, we're going to talk about motion. You see, to understand how physics works, you have to understand motion itself. When you understand the way that things move, it opens up to a big world of other ideas that we can explore. So let's get started. So as we start to talk about motion, you're going to hear some words coming up in the next day or two that you've probably heard before. So words like speed, velocity, and acceleration. These are all words that deal with motion, and we're going to use them in physics. Now, you're going to learn that some of those words may have a little bit different meaning if you talk to most people than they do for physics, but we'll get into that. Something else you should know about motion is there are different types of motion. And the type that we're going to start with is what we call one-dimensional. So we're going to start by talking about one-dimensional motion. What you'll see is that one-dimensional motion is not real common. Most types of motion have more than one dimension. But we're going to start with this anyway because you never want to start off with a super complicated example. We want to understand the basics, and then we can use our knowledge of one-dimensional motion to help us get more complex situations. All right, so what is one-dimensional motion? Well, I got a roll of tape right here I'll use to kind of show you an example. If I hold this tape up here and I drop it, it is going to fall straight down to the table that I have in front of me, and it doesn't really waver. It falls straight downward. That means it takes a single path. It doesn't go to the left or to the right at all. It's not going to move forward or backwards at all. So it's going to follow a straight line. By definition, anything that follows a single straight line path is called one-dimensional. Okay? So if I think about some examples, I want you to think about this and ask yourself, what's be one-dimensional motion? So first, let's think about a skydiver. If we look at a skydiver falling through the sky towards the ground, would you say that their motion is going to be one-dimensional? I want you to think about it a little bit before I go over the answer. Now, I would say the odds that that skydiver is going to fall in a straight line, probably not real good. If their body, if they move their arms or legs in a particular direction, they may force their way towards the left, towards the right. If the wind's blowing, it could push them one direction or another. Could it be one-dimensional? Maybe. More than likely, it's probably at least two-dimensional. Okay? They're going to get pushed in one direction or another. How about if we talk about an airplane? So if I have like an airliner you're going to take to go to New York City, let's say, you take off and the pilot gets up there and he sets his elevation and he flies along at the same elevation and the same exact course, so they're heading in the same direction at the same elevation. Do you think that would be one-dimensional? Same elevation the whole time, all right? The same direction. Well, because he's not moving left, right, up, or down, and he's flying in a straight line, that is one-dimensional. Okay? Last example, let's think about a pitcher throwing a baseball. When that baseball leaves the pitcher's hand, the baseball is traveling mostly horizontally, I would say. But when you think about that baseball or any projectile flying through the air, it is going to be under the force of gravity, and gravity is going to pull that ball down as it flies forward. No baseball moves in a straight line. It's going to move in a shape that we call a parabola. So it's going to kind of dip down as it goes because gravity continues to pull it the whole time. Okay? So what you see here, one-dimensional motion, not real common, but we're going to start with it because it allows us to build a strong foundation in terms of the way that motion works. Something else to remember about motion is that motion is relative. Now, what exactly does this mean? When we say that motion is relative, what we mean to say is it depends, motion depends on the point of view of the observer. So, if you're looking at something that you see as moving, it depends on your point of view. I'll give you an example, hopefully, to kind of clear that up. So, if you imagine that you're on a bus, and the bus is driving down the road at 50 miles an hour, if you look out the window, you see things that appear to be moving by you, going the opposite direction. But if you were standing on the ground outside the bus and you looked at that same tree or road sign that looked like was moving, if you were outside the bus standing on the ground, clearly that tree or that road sign doesn't move at all. And so it depends on where you look at it from. Another example would be if you're inside of your car. If you're inside of your car driving down the road and your cell phone's sitting in the passenger seat, and your cell phone goes off, and despite your better judgment, you're tempted to pick it up, you don't have to grab the cell phone as it zips by you or anything like that, because you're moving at the same speed that the cell phone is moving on your seat. Then you're going to think that it's not moving at all, because from your point of view, it's not. Because you're both moving at the same speed, you don't appear to be moving at all from your point of view. If I was outside the car, though, and watching you drive by, trying to pick up your cell phone, shame on you, I would see you and the cell phone zipping by me at whatever speed that you were traveling at. And one last example that might kind of blow your mind a little bit is, I would ask you, are you moving right now? The fact is that every one of us is moving right now. You see, we're sitting on Earth, and while Earth seems to be motionless, the fact is that the Earth is spinning all of the time. And so, which means it's moving, and if we're sitting on Earth, we must be moving too. But once again, just like the cell phone, we don't think we're moving because everything around us is also moving at exactly the same speed. How fast? Well, the Earth, if you look at the equator, if you go all the way around one time at the equator, the Earth's 25,000 miles around, goes around one time every 24 hours. So we're all moving about 1,000 miles an hour if our observation point were out here in space somewhere looking down on Earth. All right, so the point of view of the observer determines whether or not there's velocity there. Now, what you want to do, though, is anytime you're looking at a question about motion, you want to pick a point of view that really makes sense. So the fact is, we're all moving at the same 1,000 miles an hour, which means we don't appear to move at all. If I'm talking about a ball being thrown from one place to another, or a car rolling across the ground, it doesn't help me to say that my point of view is way out here in space somewhere looking down, because that's completely outside of what we think about when we think about motion. In that example, my point of view needs to be on Earth, because it just makes more sense. Any object that's moving is going to travel a certain distance in a certain amount of time. Now you can see this if you just look at the speedometer on your car. If we look at the units on the speedometer here, it says mph, or miles per hour, a distance and a time. So why is time important to consider when we talk about motion? Well, I want you to imagine that you have a tortoise. You guys know what a tortoise is. Let's say we have a tortoise, and this tortoise is walking across the desert, and this tortoise is going to walk 100 yards. Now, opposed to the tortoise, let's say we have a sprinter. So it's going to run the 100 meters or 100 yards, let's say, since it's the same distance. So we have a sprinter that's going to run 100 yards. Now, what would you say about the distance that these two, I don't want to say people, the tortoise and the sprinter, what about the distance that they moved? Well, they're identical. But would you characterize their motion the same way? A sprinter versus a tortoise. I don't think there's any way I would characterize their motion as being the same. But what's the difference? The difference is the time it takes for them to move that 100 meters. That time is super important when we talk about how fast that something is moving. Now, if we look at our speedometer again, we can use the units to help us figure out a formula for this. So if I look at my speedometer, our speedometer said the units were in mph, or miles per hour. We would basically say that our speed is measured in miles per hour. So what am I measuring if I'm measuring it in miles? We could also use kilometers per hour or meters per second. What you'll notice is we always put the distance over the time. Now, this is a formula you may have seen when you were in 5th grade. The relationship between these three is basically that speed equals distance over time. Sometimes we use different variables to represent these two. You'll sometimes see speed as just s equals distance. Here's a fancy variable that we use is delta x, that's our change in position, divided by delta t, our change in time. All right, so this is the first formula that you guys will see. Now, if you're in AP Physics, we're going to use formulas a lot more with numbers. If you're in regular physics, what you'll see is we're going to use formulas to help us compare values is the main thing that we're going to do. This is the relationship that we see when we're talking about speed. All right, now when we think about this formula, though, for speed, this is what we would call average speed. All right, this is average speed. And what I mean by that is that all we're doing is we're taking the total distance that was traveled and dividing it by the total time it took to go that distance. Well, we're not catching any changes in speed that would have happened here because we just said, hey, let's say that you went to San Diego, 120 miles, and it took you 2 hours. Well, I would get an average speed if I did that of 60 miles per hour. But were you really traveling 60 miles per hour the whole time? The chances are that you're not, that you're going slower at some points and faster at others. And I think you can kind of visualize this if you think about a sprinter running the 100 meters. If that sprinter takes off, the first few steps that they're taking, he's not moving as fast as he is those first, let's say, 10 yards or 10 meters as he is the last 10 meters when he's fully up to speed and he's running just as fast as he can. And so I'm not catching those changes in speed. I'm simply determining what the average speed is when I use this formula. Okay? So you can use this formula if you're doing averages. If you're looking for a speed at a particular time, it doesn't work so well. Okay guys, what we're going to do right now is we're going to do a little bit of a demonstration. In your homework assignment that you're going to see later on, you're going to have to determine the speed at which you walk. Now, if we think about the formula that we went over for speed, we know it depends upon two things. What are the two things that you need to know in order to calculate speed? Think about it for a minute. I'm going to start writing it right now. We know the formula for speed is speed equals distance over time. Or if we put it in the form of variables, we'll sometimes see speed equals delta x over delta t. The change in position over the change in time. So in the end, what we need to get a speed of anything is we need to know how far did it go and how long did it take. So how would I measure, excuse me, what would I use to measure distance? In the lab, what would we use to measure distance? Well, if you said a meter stick, you're right. So we're going to use a meter stick to measure distance, or delta x. How about time? What would you use to measure time? Well, if you have a stopwatch, you could use that, but all of us have essentially a stopwatch. It's in our cell phones. So you could use a cell phone to measure time, and you could use a meter stick or a measuring tape. Really anything you have that'll measure distance, we're going to get delta x with. So we're going to get everything set up here, and we're going to determine the speed of a little toy car. So this toy car, we're going to calculate the velocity of, but when you're asked to calculate your velocity, when you think about it, it really would be the same two variables. Okay, so we have 2 meter sticks that are laid out here. So I've got 2 meters from this point to the end of the stick down there on the floor. I got my toy car here that I'll turn on in a minute. And I'm going to start it from the very front. All right, so I'm going to have the very front of the car right at 0. We're going to go 2 meters, that's our distance. And while it's rolling, I'm going to be running my timer. All right, so we're going to do 3 trials because we never do it just once. All right, just in case there's an error, we want to catch that. So I'm going to go ahead and turn this on. And when I drop it right here at this position, I'm going to start my timer. 1, 2, 3. Okay. Our timer stopped at 5 minutes and 15 seconds. So to go 2 meters, it took, excuse me, not 5 minutes, 5 seconds, 0.15, so 5.15 seconds. Okay, that's our first trial. I'm going to go ahead and reset. First I'm going to write it. And we're going to go ahead and do a second trial. All right, turn it on again. Get it in position. Start timer. Stop timer. All right, our second trial was 5.10 seconds. So we went 2 meters in 5.10 seconds. Last trial. And start. Stop. Last trial, 5.13 seconds. All right, so we know we went 2 meters in those times. So we're going to go ahead and make that calculation right now. Okay, so here are our 3 times, 5.15, 5.10, 5.13. Now the first thing you want to do anytime you collect data like this is look at it. Make sure, I mean, this is physics, and in physics, things, if you do a particular experiment, it should turn out the same every single time. And so we want to look at these and make sure none of them are completely out of bounds. So what I see here is all three of these numbers are very, very close together. That looks like a pretty good data set to me. I don't see anything in here that's like 6.5 or 3.1 or anything like that. Everything is in the same range, so I'm comfortable with this data. What I can do now is I can go ahead and use these to calculate the speed at which the car was moving. Again, I'm just going to use my first trial. I'm going to use the formula that we know works for speed. My delta x, or my distance, is going to be the same on all three of them. It's 2 meters. And the time that it took for the first trial was 5.15 seconds. So this would give me a speed, and I'll say speed 1, since it was the first trial, of 2 divided by 5.15. All my calculators are out of battery, so I'm going to use my cell phone calculator. 2.0 divided by 5.15. I get 0.388. Now, one of the rules when we do a calculation is we need to look at the numbers we're using, and the one that has the least number of significant figures determines how many I'm allowed in my answer. Since this only has 2 sig figs, that 3.88 becomes, or 0.388 becomes 0.39. The unit would be meters per second. All right, so that is our speed for the first one. We're going to do the second and third trials pretty much the same way. Okay, it's going to be delta x over delta t. Again, we know our delta x is 2 meters. We know that our time that it took for the second trial was 5.10. And when we do that math, we're going to get a number that is very close to that first number. It may round to be the exact same number. 2.0 divided by 5.10 equals 0.392. Again, I'm only allowed 2 sig figs, so 0.392 becomes 0.39. So my second speed was 0.39 meters per second. Anytime you do a calculation like this, you guys, you've got to use units. We don't know what speed we're talking about if we don't tell people what the units are. And the last one, our third speed from our third trial is 2.0. Again, that's our distance, our delta x. Our time for that third trial was 5.13. Giving us, I'll guarantee you this is going to be 0.39 also, because that time is in between the other two. So this would be 2.0 divided by 5.13 equals 0.3898. So again, rounding to 2 sig figs, 0.39 meters per second. So that is our speed for our third trial. So I don't really need to average these to get a speed that's the average, because they're all the same number. So the speed for our toy car, all right? The speed for our toy car is 0.39 meters per second. Okay? That's how we determine speed. Now, opposed to average speed, we also have an instantaneous speed. An instantaneous speed is simply a speed that you're going to measure at one moment in time. Now, if you're going to calculate this, it gets a little difficult. A lot of times it even needs to use calculus. So this is beyond the scope of our class, but you do have a device that's going to measure your instantaneous speed. It's that same speedometer that we looked at earlier. The speedometer in your car comes very close to measuring an instantaneous speed. Now, most people think that speed and velocity mean the same thing. The truth is, they are a little bit different. And so, as you drive through town, what I would say is that speed is simply the magnitude of velocity. Big bump. So, speed basically tells me how big that velocity is. So right now, I'm going about 20 miles an hour. I'm slowing down to a stop here. So what I would say is, my speed changed from 20 to 0. So I would say the magnitude of my velocity would have changed. All right, so again, magnitude is simply telling me just how big that the velocity is. Sometimes though, just knowing how the magnitude of something is not enough. Sometimes we need more. So let's just say that you broke down in the middle of nowhere and you needed to call me and ask me for help. Well, if you would have said, hey, I'm broken down 2.5 miles outside of town, that's not going to help me. That could be any circle that's a 2.5 mile radius around Imperial. That's not really going to help me very much. What I need is more information. I'm going to need direction. You need to tell me I'm 2.5 miles west of town. All right? So this is the big difference between speed and velocity. Speed has no direction. Velocity does. Okay, so really quickly, let's talk about the difference between speed and velocity. All right, so I've got 3 numbers that are listed up here, and I want to ask you guys, are they a speed or are they a velocity? So we'll work through them one at a time. I'm going to pause. I want you to think on your own, though. Do I think this is a speed or a velocity? All right? So the first one that we have up here is 2.1 meters per second. Would that be a speed or is that a velocity? Well, if I remember between the two, remember that velocity. So what will we say about this first one? There is no direction whatsoever here. So this is a speed. All right? That's a speed. It's not a velocity. It has no direction. How about the second one here? 15.0 miles per hour east. Now, if you set velocity on this one, you'd be right. This one's a velocity because not only does it have a magnitude, 15, but it also has a direction, east. Having the direction plus that magnitude, that speed, means this is a velocity that we're looking at here. Then finally, this bottom one here, revolutions per minute. Is this a speed or is this a velocity? Now in this case, although it's telling me revolutions per minute, so it's something that's spinning, it's not telling me what direction it's spinning. And we have 2 choices. It could be clockwise or it could be counterclockwise. But the fact is, they didn't give us that information. There is no direction. So this one's a speed. All right, so this is a speed and this is a speed because they don't have direction. The middle one here does have direction, so it's a velocity. Now, if we look at velocity itself, velocity can either be constant or it can be changing. Sometimes those changes in velocity, let's talk about constant first. Constant obviously just means you're traveling at the same speed in the same direction the entire time that you're going through your motion. Okay, that's what constant would be. Constant velocity questions and issues are easier because we don't have to worry about changes. On the other hand, if we have a change in velocity, this could really be one of two things or both. Because velocity includes both a magnitude, how fast you're going, and a direction. If I change either one of those two or both, I'm going to have a changing velocity. So an example of this would be if you have a vehicle that's moving in a circle. All right, it's moving in a circle, but its speed is not changing. So let's say it's 5 miles an hour the whole time that it's moving, but it's moving in a circle. What would you say about speed? All right, if it's moving 5 miles an hour the whole time, what would you say about speed? Well, speed would be constant, but what about velocity? You could guess because velocity depends on direction, and if I'm going in a circle, that direction continually changes, then that means velocity is changing. All right, so you're going to get a change in velocity every single time if you're moving with curved motion, with circular motion. All right? So, folks, this is motion part of what we're going to talk about. We're going to take what we've learned from motion, and when we meet next time, we're going to talk about acceleration, another property of motion. So I hope you guys have enjoyed it. We will see you in the next video.